So I showed you earlier how to install Python in a computer running Windows. Now I'm going to show you how to install the modules or libraries or packages or whatever you want to call it in Python, and how to run a simple nonlinear regression application in Python. So Python, much like R, doesn't have by default all the modules that you might need installed, and you need to install them to do certain programs, to do certain applications. In Python, the module to install those other modules, it's already installed, and it's a program called pip. So let's go ahead and open our integrated development environment that we installed in the other day. So I'm going to call here IDLE. This is the Python integrated developing and learning environment. You remember, if you recall that day, we have a Windows here where you can insert code or you will see your output, but we need to open a new file if we want to start a new script which we can save for other applications. I'm going to show you how to do a simple nonlinear regression, and in the meantime I'm going to show you how to install the necessary packages. So let's go ahead and save this here as nlin.py. Remember, py is the extension that we use for Python files. To run nonlinear regression and to do plotting in Python, we need to import a few modules. To import modules on Python, you need to declare the importing procedure for the modules at the beginning of your code. This is done by the command import and then the name of your module. Let's say that's some random name here for a module. Let's run here and see what happens. If you don't have the module installed, or if the module does not exist, you're going to have the red here, the error message saying that module not found, no module name, whatever I wrote here. We're going to need a module name matplotlib. This is for plotting .pplot or pyplot. So if I run here, you're going to see that it will not complain because I already have this module installed in my computer. So there's no error message. To simplify our lives, we're going to import this module, but we're not going to import it with this name. We're going to import it as a simpler name that we can choose. We can choose whatever we want, but we can choose we're going to choose PLT. So every time I need to use this module matplotlib, I can just call PLT instead of calling this entire thing here. We're also going to need a module for data processing and for other mathematical functions called Numpy, and I'm going to import Numpy as NP. If you don't have those modules installed, you need to install them using the Python application that is made for installing those modules. I showed you that in R you can call this from the graphical user interface, but usually in Python you have to invoke a terminal window. So in Linux you have a terminal in Mac computers, and in Windows the terminal which you can use is either this command prompt here, or prompt. See, I'm opening here this little black window here, or the shell. So I have a PowerShell. It's very similar, but the PowerShell is a modernized version of the command prompt, the terminal. This is for doing shell scripts, for doing a lot of things. For, let's say it's called PowerShell, sort of because it's for power users or something like that. But let's use the older one for the sake of tradition. So let's say you don't have matplotlib installed. You're gonna go to your terminal or your PowerShell, and you're gonna use a command called pip. This is not a Windows command, it's installed with Python. So pip, it's a command to install the modules. You're gonna call install and then the name of the module that you want to install. So if you want to install matplotlib, just gonna do that. Correct this here, install matplotlib. Because I already have it installed, it's going to say here that the requirement is already satisfied. We're going to install. You're going to go ahead and install Numpy. I already have it installed as well. This is going to take a few minutes, couple of minutes in your computer. And we also we're going to need to install a module named SciPy. So I already have it installed. We're going to do something a little bit different here in SciPy. Instead of importing SciPy, I'm going to call from SciPy.optimize import curve fit. So from the module SciPy, the sub module here, if you wish, optimize, I'm going to import curve fit. This is the modules necessary for nonlinear regression. So curve fit, there's options here, and there's an example here on the Python documentation. So this should be the modules that we need to run our nonlinear regression and to plot our results. I'm going to run here just to make sure that there is nothing weird about it, no error messages. So everything's okay, no red warning here. So we have imported our modules. This needs to be at the beginning of your code because you're gonna use procedures from these modules here and they need to be declared at the beginning of your code. So first of all, I'm gonna put a comment here and this is gonna be our data. You can import data using from outside files, from files outside of your program, or you can import files from the internet. You can import data from the internet. You can scrape data from internet. You can use other modules or formats for data importing. But for simplicity, let's just input our data here as variables in our program. What we are going to do is we're going to use a very simple example here from nonlinear regression for a page for the Gauss-Newton algorithm for nonlinear regression on the Wikipedia. We're not going to be use the Gauss-Newton algorithm. You see that for the curve fit of SciPy, the method here is LM, which is the Levenberg-Marquardt algorithm. We're gonna be using the default. The Levenberg-Marquardt algorithm. It's pretty good for. It's usually pretty good for nonlinear problems for hydrology and soil physics problems. Water retention curve, mechanical resistance curves, and hydraulic conductivity. It's pretty good for these types of applications. So that's why I am using it here. So I'm going to declare a variable s, which is from the example key here of Wikipedia. To declare the variable here in Python, I'm going to declare using Numpy. So I'm going to call it NP. I'm calling Numpy. And I'm going to use the function array of Numpy. And then the data goes inside brackets here. The regular brackets and the square brackets. For simplicity, I'm just going to copy here from Wikipedia, copy the data from Wikipedia, paste it here. So this is the s, the x variable, and the function that we're going to fit is this function here. The rate y variable here is a function of s, and vmax and km are fitting parameters. So our objective here is to fit this function using nonlinear regression and find the best fit values for those two parameters. On our array here, just do a little correction here. We need to put commas between the values here. So don't forget to put commas, and don't forget the order of the brackets here. So we have a regular bracket and a square bracket. I'm going to do the same thing now for the y variable. You could technically call it y and x. It doesn't really matter. You can call it whatever you want. I'm just calling here to be through our example. So I'm going to just go ahead and copy this here again, the rate. Let's just paste it here. And don't forget to put the commas between the variables. So if everything is okay, Python will read the variables in the program without any issues. So let's just run this here to see if everything is okay. So if you have any kind of data that you want to fit, you need to put the data here in this format. So as I mentioned, you can import data in other formats, but this is probably the simple way of inputting data if you're a beginner in Python, and it's pretty similar in R as well. I might have other videos showing you that. So let's do a simple plot here to show you the relationship between those two data. So this is comments, this is a comment. We're gonna need the PLT or the matplotlib.pyplot module to plot. I'm gonna use the command plot here, and I'm gonna put s. I'm gonna plot s, the x variable, and rate, the y variable, and the symbol I'm gonna use is the star. I'm declaring the symbol here used between the quotations here. If I do this here, you're gonna see that really nothing happens because I need to call the plot, or I need to show the plot. So calling matplotlib again, plt.show, or show the plot, and let's run this again. So this is our observed data. Got it from the Wikipedia, some form of reaction rate as a function of some substrate concentration. So you see these in biological science, in chemistry, soil science, there's those kinds of plots are very common. What we need to do is to get the best fit line of this curve by fitting that equation to the parameters, or to the initial parameters. So we're going to have to first of all declare the function that we're going to use. So function, I'm going to use def, which is a Python function for defining a function. Func is the function that we're going to define. The function is going to be a function of s, which is a variable, and the parameters, which are what are the parameters in this function? Vmax and km. It could be anything, but let's call Vmax and km, so two parameters. So if you have a water retention curve, or a conductivity function, or a mechanical resistance function, this is where you declare your function. So if you change here, you can fit different functions to this data. So when I call func, that is defined here, you can call this different names, but when I call func, this function will return the equation. So the equation that we want to fit is Vmax times S divided by Km plus S. Better, Vmax times S divided by Km plus S. Okay, so we have Vmax times S divided by Km plus X. Okay, so whenever I use func and I declare the parameters here, it will return me this function. You will get me the values of the function. So you declare your equation here, you declare the x variable here, the independent variable, you need to declare parameters here. If you have 5 parameters, you declare them here, and then you put them here in your function. So now we need to fit our data. So for fitting our data, we're going to use this curve fit procedure. First, we need to declare a vector, or a data set, or an array that will store the values of the fitted coefficients and the covariance matrix of the parameters or the fitting. So what we're usually interested in, it's in the value of these parameters here. So this is going to be equal to curve sub fit func I need to declare here S, Vmax, and Km. Let's try to run, see if there's any problem here. So we need the function here, and then we need the X data and the Y data. Okay, so this, hopefully this will work now. Okay, so it didn't combine, so it probably worked. So now what we have, it's only the observed data. We want to use now the fitted parameters to so we can plot the observed data and the fitted model. To plot the fitted model, we're gonna do this here again. But now we copy this here again. We're gonna draw a line on the plot. We're plotting the points, and we're plotting another line here. But this line is going to be S, the X variable, and the func. We're going to use the function here to predict using our parameters. So Vmax, or better, we already have the values of the parameters stored in this popped function here. So we're just going to need to call this popped function to do this plot. So we're going to need a line here. So I'm declaring this is the symbol for the points, and this is to say that we want to fit a line. So let's run this again. Let's correct this here. So now you have the observed data and the best fit line. Okay, let's just minimize this here so I can show you something. You see that everything's okay. We corrected the zeros here, but it's not showing the values, the best fit values of the parameters or the parameters. If you want to see the best fit values, you have to call for print, or to display the values of the coefficients. So I'm gonna just say here, these are the best fit values of the coefficients. Okay, these are the best fit values for this. It's just a comment that will show you when you see the output here. So just run this again. So we have 0.31 and 0.55. If you check here the Wikipedia, these are the values that they found, 0.30, around 0.30 and 0.55. So it's pretty close to what they have there. So 0.361 here and 0.55. So it's very close. It's essentially, mathematically, is essentially the same as they found it there. But now, if you look at the graph, there's a problem here. You have those it's not like discontinuities, but you have those wrinkles here on your graph, and you want a smooth graph. This is because you have a low number of points for your X variable. So since you already have a function that was fit using those parameters, you can generate that data from the function, and then you can plot a line for a very large number of functions or of points, and then your line will be smooth. You could smooth this line as well, but using spline or something else, but that would be much more complicated. That would add complication that we don't want right now. So I'm going to create a new variable, which should be simulated s values. It's called simulated s, and I'm going to call a function in numpy, which will create a range of values from 0 here, from 0 to 4, but I'm going to put much more points than the original data. So I'm going to put an interval here of 0.01, and now here I'm going to simulate. I'm going to plot the observed data, or better, the fit data in terms of this new data set that I'm simulated, and I'm going to use it, the fitted function, to simulate, to estimate the y values from these simulated x values. It doesn't really change anything, but you see that the results will be much better. It's okay. Let's do this again. You see now that the line is much more smooth, so our graph is a lot prettier. And to improve our graph here, you can put labels for the x and y axis. Actually, there's a lot of things you can do. I'm just going to show you a very simple example, but you can configure that. Matplotlib is very, very powerful. You can do a lot of things for your graph. I'm going to run it here. And if everything is okay, here's your graph with your axis. You can save it directly here on your computer, and you can use commands here to export it as PDF or EPS or JPEG or many other types of file formats.